Okay, in this video we're going to go ahead and continue talking about the different properties and parameters that control this rigid body in XSI. So the next set of parameters is the dynamics initial state parameters. We're going to skip those for the moment because we'll talk about those later when they come into play and when they make a lot more sense. Right now we're going to jump down to rigid body properties down here, and this is by far going to be one of the most important parameter sets that pertains and controls your rigid body here. Okay, now the first option, mute, here temporarily turns off the rigid body so it won't simulate. So if I hit play, you notice that that cube just sits there. It doesn't fall with gravity, it doesn't move, doesn't react, doesn't do anything. It's just kind of frozen there in place. If I unmute it, it's back into action. Now this passive parameter, something very interesting to note. If you remember when we went to create menu and we went to rigid bodies, there was two types of rigid bodies that we can create: active rigid bodies and passive rigid bodies. Now you'll probably remember that each one's a little bit different than the other. Well, in reality, they're actually the same. When you create an active rigid body, you're really creating this rigid body here with this passive parameter turned off, so it's unchecked. When you create a passive rigid body, it creates the same exact rigid body. The only difference is that the passive parameter is checked on for passive bodies or passive rigid bodies. So that's the only difference between a passive rigid body and an active rigid body, is the fact that this option here is either checked on or checked off. So that's just something to take note of and very interesting to understand. Down here under collisions, we have this drop down box which allows us to choose what this cube is going to go ahead and collide with. By default, it's set to everything. So if I go ahead and I zoom out here real quick and I hit play, the object collides with the other object. So the cube falls on top of the table. Pretty simple. Pretty much what you'd expect. Now if I switch this to nothing, what happens is that the object still falls. It's affected by gravity and other forces, whatever forces are set up for it, but it'll fall through the object. It will no longer collide. And if we go here and we switch to another option, the layer option, we can actually set up layers. So the object will still collide, as you can see. But we can set up layers. We can tell it to only collide with a specific object or a specific number of objects. We can go over here to this input field here and we could type in the layer that we want. So say for example we switch this from layer 0, which is the default, to layer 2. Okay. Now if I hit play, you'll notice it still collides. This is because I need to set up the layer collisions with this object here. See, the table object is right now set to collide with everything. But if I switch it to layer and I leave it at layer 0, you'll notice that the object, the cube, falls right through it because they have two different layer identification numbers, so they won't collide with each other. As soon as I switch this to layer 2, now both objects have the same layer ID number, which will allow them to interact and collide with each other, as you can see. Now they actually collide and interact with each other because they're both set to layer 2. So I'll switch this back to everything. I'll select this guy over here and switch this one back to everything as well. So now they collide with each other, as you can see. Okay, down here we have a very important option down here. It's the collision type. You can actually select different collision types for your object. This is going to determine this yellow collision object here. Now, let me zoom into this object here just so you can see what's going to happen. Okay, right now you can see it has a yellow wireframe. This wireframe, in fact, is not the wireframe of the cube. It's a wireframe that represents the collision object of this cube. Right now it's set to a bounding box. We can switch it to a bounding sphere, and you notice that the yellow object now looks like a sphere wireframe. We can also switch to a bounding capsule, which looks kind of like a pill that you would take maybe for a cold or something. So that's a capsule shape. Then we have a convex hull, and the convex hull tries to take the shape of the actual object. In this case the object's a cube, so the convex hull tries to take the shape of a cube. And you can see it has these triangles here, all these lines. It's triangulated. Okay, right now it's at subdivision level 0, and we'll talk about that more in a moment. Then we have actual shape, and in actual shape you notice there's no more yellow hull, or no more yellow collision hull. Edit that out of the video, edit that out of the video. Starting again in 3, 2, 1. So you'll notice when we switch to actual shape that the yellow collision hull disappeared, went away. This is because now the actual shape of the object is being taken into account when calculating the simulation. Okay, so we have all these different shapes with different options. What do they mean? If you use a bounding box, bounding sphere, or a bounding capsule, those are the most optimized bounding hulls to use. Those shapes will allow you to have a very quick simulation. They're very optimized. So they allow you to simulate very fast. The downside to them is that they're not accurate at all. For example, if I use a bounding sphere for this cube, my simulation is not going to look right because the cube is not going to bounce correctly on whatever object it hits. Essentially, this yellow sphere around it is going to determine how it collides and reacts with the environment and the different objects that are set up as obstacles in the environment. So it could look pretty fake. For example, if this point up here lands on top of a table, you're going to have this empty space between the surface of the cube and the table. So it's not going to look very realistic at all. If I switch over to a bounding box, however, since the bounding box is more similar to the shape of the actual cube, now the simulation is going to be very accurate. But of course, not on every occasion are you going to want to simulate cubes. Maybe on some occasions you want to simulate a character or some other object, like say a table lamp or something, and that's going to have a totally different shape than a cube. So a cube bounding box in that case is not going to work very well. Then we also have a capsule, which is just another option, another type of shape that you can use. If it's similar to the shape of the object you're trying to simulate, then you might be able to get away with it. So the trick here is to try to use one of these bounding shapes when you're trying to save time, when you're trying to calculate these simulations as quickly as possible. But just make sure that the bounding shape matches very similar to the actual shape of the object. If you have a complex object, you can use convex hull. Convex hull is going to try to imitate the shape of the object, but it's not going to do it exact. So it's not as accurate as using, say, actual shape, but it's more optimized than actual shape, which allows you to create fairly quick simulations and fairly accurate looking. So they'll look pretty accurate and they'll simulate fairly quickly. So it's kind of a balance between the two. It's kind of a balance from bounding shape and actual shape. So you get some speed and some accuracy. And down here, if you're not getting the accuracy that you want, you can increase the subdivision level. Now the more subdivision levels you use, the more complex this hull becomes, this yellow hull, and the longer the simulation is going to take. But the more accurate it's going to look. So increasing subdivision level decreases simulation speed, but it increases the accuracy of the simulation. Now if we choose actual shape, now we're using the actual shape of the object to simulate. In this case it's just a cube, so it's not going to slow down the simulation practically at all. But if we were using a more complex shape, then we're going to have a problem. Then using the actual shape is actually going to take a pretty long time to calculate. Much longer than using, say, convex hull, and definitely much longer than using bounding, any of the bounding shapes. Okay? Now, if you're using actual shape, use a low setting so that it simulates faster. With a subdivision level of 0, this is going to simulate very fast. If we use a medium setting, a high setting, or the coffee break setting, now the simulation is going to take a very long time, especially if you use coffee break with subdivision level here very high, like say 5. That's going to take a very long time to simulate. Hence why they went ahead and named this option coffee break, because you're going to be taking a coffee break, and in some cases maybe even an entire lunch break. Alright, so be careful with that. I suggest sticking to the bounding shapes if they are very similar to the actual object you're simulating, or use convex hull, which gives you the best of both worlds. It gives you speed that's very close to bounding shapes with accuracy that's pretty close to using the actual shape. So it's just something to take into consideration. Down here we have some surface properties. We have elasticity, we have static friction, and dynamic friction. What these parameters do, they determine how your object here, in this case this cube, is going to interact with other objects when it bounces off of them or when it's sliding on the surface. Now the elasticity here controls the kinetic energy of the object. That is to say, this parameter is going to go ahead and control how much of the kinetic energy is lost when this object makes contact or collides with another object. So let me just go ahead and show you how that works. If I hit play now, you notice how the cube bounces. It's very bouncy, kind of like a rubbery material, kind of like a rubber ball, even though it's a cube, so it's kind of weird to say that. Okay, if I lowered the elasticity down very low, and I try this again, you'll notice that the object just lands almost like an anchor from a ship. It just smacks right onto the floor and doesn't even really fidget or move. It barely moves at all. It just lands, bam, and just sits there. Doesn't bounce around a lot. So as I increase this, I can see that it gets more bouncy. Now it bounces a little bit more. So it looks like it's heavier actually. It looks more like you're dropping, say, an exercise weight or something like that, or maybe a shoe, something that's not going to bounce around a lot. And if I increase this to very high numbers, this object's going to be very, very bouncy. Kind of looks like a rubber ball or maybe a tennis ball or something like that. So elasticity is a very important parameter that's going to determine the characteristics and the actual way that this object is going to interact with other objects in the scene. Now the static friction is going to determine the amount of friction or resistance when an object is sitting in place. That is to say, when the object is not moving. If this cube is sitting on top of this table and it's not moving and the table suddenly starts to slant and this object starts to slide off, the more friction that you have, the harder it's going to be for that object to slide off. It's going to be almost like if it's a rough surface that's not very slippery, that is holding onto the object with a lot of static. Okay? The lower we reduce the static to, the more the object's going to be able to freely slide on top of the surface. So it imitates something more of, say, an oily surface, and now the object can just slip and slide all over the place. Dynamic friction is going to determine the amount of dynamic or kinetic friction of an object. That is to say, when an object hits another object or rubs up against another object, the more dynamic friction you have, the harder it's going to be for one object to slide across that other object. So it's almost going to be like taking two stones and rubbing them against each other. There's a lot of resistance there because there's a lot of dynamic friction. Now, if you lower this, there's less dynamic friction. So it's kind of like taking two marbles and rubbing them against each other. They just slide right across the surface because they have a very smooth surface with very little dynamic friction. So these parameters here control those different types of frictions like they would exist in real life. Okay, so that's going to do it for these rigid body parameters here. We'll talk about more of these parameters in other videos down the road, and we'll get into some other parameters here and how to control these different properties to control your dynamic simulation.